And now for the ultimate challenge. We have a system, first order system here, which is almost general. Notice that there is no t in the right-hand side. So this is an autonomous system of differential equations. But other than that, we can expect anything on the right-hand side. In fact, we can expect that this system is not linear to make our life more interesting. We want to find stationary solutions and then classify them, because there are 6 types that we are really interested in. How do we do it? Well, stationary solutions, these are found easily. We take the right-hand side and make it equal to 0 as a vector, because this is a vector, the output is a vector. Now, the fact that f is most likely not linear makes this situation very interesting, because there could be 1 solution, or no solution, or 13 solutions, anything can happen. The fact that the system is autonomous, that there is no t in the equation, actually makes it more likely that we do find some stationary solutions. So let's be optimistic. Let's say that we found some and we pick one of them. Here it is, ys, for stationary, obviously. That's a stationary solution. But perhaps we can call it a stationary point, because now we are adopting the point of view of orbits. Okay? And now, classification. We want to know what's happening with orbits around this stationary point. Or, in another way, we want to know what's happening with solutions around this stationary solution when we see it as a constant function. Of course, we could, sketch the vector field using this right-hand side. We did this before, and it did send some, messages, but they were not reliable. That's the problem. So we need something which is mathematical, reliable, complete information. Well, to get there, we look at this equation again and we ask, what is the story behind it? And well, there may be more stories, but there is one which I'm interested in right now. It's a feedback equation. You have some quantity that you are really interested in. In fact, you have like n quantities, but we lump them together into one vector. So let's say you have one quantity, multi-dimensional quantity, and you want to know how it changes, how it behaves, how it develops. And the equation says, if you want to know how this quantity changes, you just look at it right now. That's the current situation. You put it into this formula f, and you get your feedback. You get information how your quantity changes. Now, when we are doing classification of a stationary point, we are not really interested in the general behavior of solutions or orbits. We are just interested in what's happening when we are nearby, which means when y is close to ys. And that's a familiar situation. We want to know how some function works near a specific point, and we are not really happy with the function because it's general, it's complicated. So we replace it with its approximation. Let's say a linear Taylor approximation. That's a good idea. That sounds really good. So what happens? Well, we have this derivative, but instead of equality, I'm going to put this really imprecise approximation mark, and I replace this function with its Taylor expansion. So there's this absolute term. I'm putting ys. That's my chosen center for the approximation, for the Taylor expansion. I'm putting it into f. And then there will be this, in quotation marks, derivative, which in this case is the Jacobi matrix, again at location ys. And this multiplies the vector y minus ys. So this is really like a Taylor polynomial for ordinary function, just moved into more dimensions. Now, if this function of f is not too wild, then this approximation and the original function should essentially provide the same feedback around ys. So it makes sense to replace them like that. And notice that ys was a stationary point for this right-hand side, and it is also a stationary point for this new equation that we have here, because fys is definitely 0, and when we put ys here for y, we get 0 as well. So this new system has the same stationary point, the center ys. This new system is called linearization of the original system. And that's a very important notion. Let me put it here. When we go from here to here, this is called linearization. And of course, it's just local. it makes sense to consider this linearization only when we are nearby this stationary point ys. But that's all that we need right now. Okay, let's have a look at it again. Y vector derivative is about, well, fys, that's a 0. We talked about it, 0 as a vector. So I split this into two parts. There will be the Jacobi matrix f at ys, multiplying y. Then there will be minus the Jacobi matrix at ys, multiplying ys. Now, Jacobi matrix at a specific location, that's a constant matrix. This is a constant stationary point, so this is a constant vector which we typically call b. This is our unknown function, and that's a matrix. And again, it has constant coefficients. It's a constant matrix. So we can call it A, and when I look at this, I can actually see a linear system, which is not homogeneous, perhaps. We don't know. This could be 0, for all I care. I don't really care. So, if I want to know how this stationary point works, how the orbits around this stationary points look like, how they behave, all I need to do is pass from the original equation into my linearization and ask, okay, what's happening here with my stationary point? And the answer is, the matrix A decides. I just look at the eigenvalues and I have my answer. And that's the whole secret. Let's try it. Our second example goes like this. The derivative of x, the time derivative, is y squared minus 1, and the y derivative with respect to time was y minus x, I think. That was the system. What is the feedback function? The right-hand side. The function takes values x and y and spits out the vector y squared minus 1, y minus x. Okay? No problem there. So, if we want to approximate this function at some center, we are going to need the Jacobi matrix. Jacobi matrix at xy looks like, let's see, I take the first component and I differentiate it with respect to x and with respect to y. So the derivative with respect to x is just 0, and the derivative with respect to y is 2y. So far, so good. The second component, again, differentiate with respect to x, with respect to y. So derivative by x yields -1, derivative by y yields 1. So that's the general formula for the Jacobi matrix of this particular function. Now, let's have a look at stationary points. Now, if you remember, we had two stationary points, point 1, 1, and point -1, -1. And if you want, you can try it again. You make this one equal to 0, and you get 1, -1 for y, and then you make this one 0, and you find that x is the same as y. Here we are. So, around the point 1, 1, we take this equation, and we replace the right-hand side with the Taylor approximation. We do this linearization. And what is the matrix in this Taylor approximation? What is this new system? How does it look like? What is the matrix A? Good question. Matrix A will be the Jacobi matrix at the location 1, 1, which is, let's see, well, we are putting 1 here. 0, 2, -1, 1. So that's what we call A in this linearization. What are the eigenvalues? Good question. Well, let's see. I find determinant of minus lambda 2, -1, 1 minus lambda, which comes to, okay, lambda squared minus lambda minus plus 2. And I'm asking, does it ever get to 0? Get to be 0? Well, let's see. Let's split it. This is a school problem, so I expect something nice. Lambda here, 2 at the end. So 1 here, 2 here. Either 2 minuses or 2 pluses. Okay, they do not work. So factorization didn't really help. I have to go to the formula. Lambda is, let's see, division by 2. Minus 1 is plus 1. Plus minus square root 1 squared minus 8. So this will be 1/2 plus or minus square root of 7 over 2i. Actually, I don't really care very much. What I care about is, first of all, the real part. That's here. The real part is positive. What does it mean? Well, it means that the solutions will be going away from the origin, or in other words, when I shift the situation away from my stationary point 1, 1. So it will be unstable. This I can see right away. I can also see that the imaginary part is not 0, so there will be some rotation happening as well. Well, unstable focus. That's my conclusion. And in fact, we guessed it before. That was our guess. But we were not sure. And now we can be sure, because the linearization confirmed it. Let's have a look at the picture. Let me recall how the situation looks like around the point 1, 1. That's the picture that we had before. And when I look at these arrows, they do seem to go around in circle, but outwards. It's like a fan. It's a spiral which is unwinding. So yes, this picture, as I see it, it goes around to the right like that, clockwise. In my picture, it's counterclockwise over here, but this doesn't really make any difference. Okay? The tendencies are the same. It's unstable focus. Okay, now for the second picture, just out of curiosity, for -1, -1, we had this. That was the slope field. So there are those bending orbits going around, never reaching our stationary point in the middle. They seem to be approaching and then going away, and some of them are just going away. So going back to my classification, I would say that this is a prime example of a saddle. This looks like a saddle. Let's see whether we confirm it. So our matrix A for the linearization is the Jacobi matrix with -1, -1 as the center. I substitute, and I get -1 here. So it's 0, -2, -1, 1. That's my Jacobi matrix. Let's find the eigenvalues. Determinant of minus lambda, -2, -1, 1 minus lambda is lambda squared minus lambda minus 2. Could this be 0? Good question. Well, I hope now it works. Let's see. Lambda here, 1 here, 2 here, minus here, plus here. Is that right? Yeah, works out. Lambda is -1 and 2. So there are two solutions in my fundamental system. One solution is based on e to -t, and such solutions go towards the center, towards the origin. That's the good news. Then there are some solutions that are based on e to 2t, and they go away. So it's a mixed situation. Some solutions are going towards my stationary solution, and some are going away. That's exactly saddle. Let me put it here. Or one can simply remember the chart which I've been drawing here. If you remember, there was a chart, 6 situations, and each of them has a description given in terms of eigenvalues. So if the eigenvalue is complex with positive real part, you get unstable focus. If you have real eigenvalues which have distinct signs, you get a saddle. Wonderful. So as you can see, it really does work nicely also for nonlinear systems. This linearization is the key. You can also use it to approximate solutions when they are near this center. And it need to be a stationary point, need not be. Okay? So if you just have some point that is really of interest to you, and you want to know what's happening around, you use it in this Taylor expansion, and you approximate your system by a different formula, but then you have to do some more work. It's not enough to just look at the matrix. But this is a very fruitful idea, linearization. Very extremely strong, I would say. Very good tool. Let's go back to this example. You may say, okay, wait a second. Okay, we didn't really see any linearization in action, did we? I mean, I took the point 1, 1. I found the Jacobi matrix, and then I just jumped right into the conclusion. So what can we say about this linearization? Let's have a look at it. Our function f, the right-hand side, gets replaced by the following thing. And I look at the formula over here. I take my Jacobi matrix with the center substituted into it. So it will be the matrix O, 2, negative 1, 1. And this one multiplies the unknown vector, xy. Then there is minus this matrix multiplying the center, which is my stationary point, 1, 1. How much is it? Well, let's see. Over here, I'm getting 2y. I'm getting minus x plus y. And I'm subtracting 2, 0. So this is really 2y minus 2 and y minus x. What does it mean? Well, it means that this system that I have over here gets replaced by another system of differential equations that have this as the right-hand side. Do I have some room over here? Yeah. Let's put it here. So for 1, 1, the linearization works like that. X dot is 2y minus 2, and y dot is y minus x. Now, I commented earlier that the second equation is linear, so the linearization just kept it. It just changed the first equation. Now, we have a new system. Old system, new system. They are not the same, definitely not. But 1, 1 is a stationary point for both of them. And I hope that nearby this point, the solutions behave the same. And I can actually check, because I can find solutions here, I can find solutions here, or rather orbits. Again, I use the vector field for it, and I can compare. This will be interesting. Let's have a look at it. So here is my code. What you can see in this picture, perhaps I can enlarge it still a little bit more. The blue arrows, that's the slope field for orbits on the neighborhood of 1, 1 for the original system. So this is blue. And this linearization, based on this formula, based on this approximation, is in red. And you can see that when you stay near the point 1, 1, which is the center of our attention, then the red and blue arrows, they agree essentially, they match. But when you go away, they start being different. And like over here, they are leading in totally different directions. They're almost perpendicular. So that's to be expected, because linearization is local. But you can notice that when you are nearby the point 1, 1, then there is a perfect match. So really, this linearization does provide good information, relevant information about the original system, as long as you stay close to 1, 1. Okay, just for the sake of completeness, let's have a look at the point negative 1, negative 1. So the right-hand side now gets approximated by the matrices 0, negative 2, negative 1, 1. I'm multiplying by the vector xy. So we are here. And now I'm subtracting our matrix. Zero, negative 2, negative 1, 1. Multiplying our center of attention, which is negative 1, negative 1. How much is it? Well. Here I am getting negative 2y minus x plus y. I'm subtracting the vector, which is 2 and 0. So this is negative 2y minus 2, y minus x. So when we stay close to negative 1, the original system gets replaced by a new system which looks like this. X derivative is negative 2y minus 2, and y derivative is y minus x. I can see it from there. And again, let's compare the two systems. Here we have another picture. Again, the blue arrows, that's the original system. And we see orbits, not the solutions. Let's be careful. These are the trajectories of the solutions. And the red arrows, that's the linearization. And just as before, when we go away from this point, -1, -1, then the red and blue arrows, they start getting different. This is to be expected, but if we stay close, they match perfectly. They are exactly the same arrows. So this system and the original system, they behave exactly the same when we are nearby, -1, -1, and it all makes sense, okay? And that's the main message of this linearization business. So we can do classification, even for general systems. Let's have a look at them. But before we leave, one more picture. This is the slope field for orbits for the original system, and I just put some numerically calculated orbits so that you can see what's happening. On the right, there is this unstable focus, the outgoing spirals, and we see some solutions. Some of them are going around almost all the way, and some of them are going around just a little bit, and then they leave, they go away. And on the left, -1, -1, there is the saddle, and the solutions are going from the lower left corner, and they are sort of splitting. They are going around this saddle. They don't want to go there. Okay? So that's a very nice picture. As I said, this is a system of differential equation that looks deceivingly simple. It looks very nice, but it's complicated. It cannot be solved analytically. The shape of orbits cannot be determined analytically. And as you can see from the solutions, there are all kinds of different behaviors. This is really nice, really interesting. So even a very simple system of differential equations can actually, let's say, carry in it all kinds of different behaviors. This is really a very nice system. And that's the happy end. There is essentially nothing more to add. This linearization, a perfect tool, it allows us to classify even nonlinear systems. Of course, this all works very well also for, let's say, systems of higher dimension. Because if you have more equations, like 3x3 system, 4x4 system, you simply find the Jacobian matrix, you find lambdas, and you look at them. What signs do they have? Do they have imaginary parts or not? And essentially, these pictures can be also imagined in 3D, in 4D, and so on. Like in 3D, the solutions are cycling around your stationary point, or perhaps they are going inside along some curves, or perhaps going outside. So all these 6 situations, they make perfect sense also in more dimensions. So this classification is done not just for 2x2 systems, but also for higher dimension systems. And that's it. Now, if you are curious, I'm going to do a bonus. I'm going to do a thorough investigation of 2 systems that I can solve, actually. So these will be linear systems. And we will see how those theoretical, let's say, musings and those theoretical expectations actually reflect in an actual situation. So this is not really all that necessary, but I think it's a nice and compelling story which shows how these things really work. Here is our first example. A 2x2 system, is it linear? Oh yes. 2 linear combinations on the right. It's not homogeneous because there are some extra right-hand sides, but they do not feature t. They are just constant, so there is a chance for finding a stationary solution. Let's have a look. I take the right-hand sides and make them equal to 0. I'm finding stationary solutions. Well, -2y plus 2 is hopefully 0, and 3x minus 7y plus 4 is also hopefully 0. Let's see, from the first equation, y should be 1, definitely, no other way. I put it into the second equation, minus 3 divide x is 1. So I can say that 1, 1 is an equilibrium or stationary point. Or if I want, I can talk about solutions. I can say that y, s, t is equal to 1, 1. That's a stationary solution. Or perhaps you may want to say that x s t and y s t is 1. That's a stationary solution. And of course, I should put the region of validity always. And also here. A small one. Okay. What do we know about this equilibrium? Well, first of all, we can sketch it. 4 stands over here. Well, how much room will I need? Let's be generous. X and Y. Here is 1 and 1. Okay, that's our stationary solution, or equilibrium or stationary point. Now, classification. Classification needs to know the matrix of the system. What is the matrix of the system? It's actually 0, -2, 3, -7. Now we find the determinant of minus lambda, -2, 3, -7 minus lambda, which is essentially lambda squared, plus 7 lambda, that's a lot of lambdas, plus 6, and this is perhaps 0. Well, let's see, are we lucky? Lambda, plus, yeah, plus 2, plus 1, plus 6. It was either 1, 6 or 2, 3, or perhaps we go to the discriminant formula. 1, 6 does work. 1 times 6 is 6, 1 plus 6 is 7. Yeah? Our lambdas are -1 and -6. So let's make some conclusions. We can say, based on our previous theorem, that 1, 1 is a stable stationary solution. How do we know? Because the lambdas are negative. We had a theorem about it. You just look at lambdas and the signs they decide, signs of the real part. But in this case, these are real eigenvalues, so no problem there. Classification. If you remember the chart that I draw, negative lambdas, that's the upper left corner, stable node or stable node. But you can sort of visualize it. When you have these lambdas in the solution, you will have two exponentials, e to -t, e to -6t. They both go to 0. So the solutions will be going towards the origin, and then we shift it to 1, 1. So this is stable knot or node. You can choose whatever you want. Okay, so the classification is done. But you say, oh, wait a second. Didn't we ask for more? Didn't I promise more? Well, yeah, let's investigate. We know that the solutions actually go to the stationary point 1, 1. They should go there. But how? That's an interesting question. So let's ask about a general solution. Well, general solution consists of two components, a particle solution and the general homogeneous part. Particle solution, where do we get it? Well, we already have it. This is a stationary solution, and therefore it is a solution. We can use it as YP. Wonderful. Now we just need to figure out the solution of the associated homogeneous system. So we go to lambdas, we find eigenvectors, we put it together. No big problem, no big deal, in fact. So when lambda is -1, then I put -1 for lambda here, it becomes 1, -2, 3, -6. Now the second row is triple of the first one, which is okay, that's how it's supposed to be. It's supposed to be singular, so probably I did make a mistake so far. This means that the equation is v1 minus 2v2 is 0, and therefore I can find eigenvector. I put 1 for v2, and then v1 will be 2. So I have lambda, I have eigenvector, and I can use it to create the first vector in my solution, or rather in my fundamental system. It's e to -t, because lambda is -1, and the eigenvector. And this is taken a times. And then b times the second component in my fundamental system. So let's see. When lambda is -6, that's a big number. Usually at school you don't get such huge eigenvalues. You get like 1 or 2 or 3 at most. Okay, let me write it properly. So it's -6. I'm putting a -6 here. I get 6, -2, 3, -6, -1. And now the first row is double of the second row. So again, it's a single matrix. And I use the second row for my equation. 3v1 minus v2 is 0. Let's see, I will put 1 for v1, and I get 3. When I have a new choke, I get 3 for v2. Okay, here's my lambda, here is my v, 1, 3, e to negative 6t. T, let's say, greater than or equal to 0. I don't really care much. Okay, I look at it and I say, okay, that's my general solution. What happens when I send time to infinity? Well, then in the solution, exponentials go to 0, and this whole vector tends to 1, 1. Well, this just confirms that my stationary solution is actually stable. So, no big surprise. Now the good question. How does it go there? How does this y go to 1, 1? Let me focus on the homogeneous part. In the homogeneous part, we can see two components. And we know that when two exponentials meet in a linear combination, then the one with larger exponent is dominant. So I'm going to factor it out. I'm going to factor out e to negative t, and I get a times 2, 1 plus b times 1, 3 e to negative 5t. Now what happens when time goes to infinity? Well, this part goes to 0. And therefore this whole bracket starts looking like a times 2, 1. If a is not 0, one should be careful. And of course this part goes to 0, but this is not surprising. We are interested in direction. So let's split two cases. Case number 1. What if a is 0? Well, if a is 0, then my homogeneous solution is just a multiple of the vector 1, 3 multiplied by the exponential e to negative 6t. Because I can go back to this formula. This becomes 0. I'm just looking at this. So my solution is scrolling towards the origin. And when I put it here, it's scrolling towards 1, 1 from the direction 1, 3. That's interesting. Direction 1, 3, how does it look like? We put one part here and 3 parts here. It's a fairly steep, I guess, 1, 2, 3, I guess like that. That could be the direction 1, 3. And that's the direction of the orbits for this particular type of a solution. So if you start somewhere on this line, and it doesn't really matter where, the solution will be going along this ray towards the stationary point 1, 1. Which brings us to an interesting question. What happens if b is 0? If b is 0, then these are just multiples of the vector 2, 1. Vector 2, 1, how does it look like? It looks like this. 2 and 1. It's this direction. So these are the two basic directions that lead towards our stationary point. This is direction 1, 3, and this is direction 2, 1. And let's make a note that this one works with b, and this one works with a. What happens if you have a vector which has both components, which means that's the case too when a is not 0? Then when t is really, really large, then in this bracket, the second part can be ignored, and the solution is approximated just by the first part. So it will be a 2, 1 e to negative t. So if you start at some other place, here, 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 then the solution at the start can go in all kinds of ways. But eventually, as we approach this stationary point, we should be approaching it from direction 2, 1. So I expect something like that, and something like that, something like that, something like that. So this direction 2, 1, it's privileged. If you want, you can figure out the formula for this line, and you can easily figure out which one it is because it's given by a vector formula over here. over here, or it's given by parametric formula if you want to parameterize it. No big deal. This one is actually given as y minus 1 is 1/2 x minus 1. That's this line. And this line is y minus 1 is 3 times x minus 1. Okay, so this is just ordinary analytic geometry. No big deal. But this is an interesting picture. We know that it's stable knot, but we actually see that there is more to it. There is one privileged direction which is attracting all the orbits, with exception of those orbits that start on this other direction. So this poor guy, 1/3, if you start there, you stay with it. But if you start even a little bit away, this guy overwhelms the direction. This guy overwhelms the tendency. Even if you start just like here, you will go this way. Is that true? Well, let's have a look at it. I have a maple code, and I have some vector fields for you. Let's see. The green curves, the green lines, that's exactly the two basic directions, and that's actually solutions. I asked directly for solution which starts at this place, and I asked for a solution which starts at this location, this location, this location. So I didn't cheat. I didn't ask computer to draw two straight lines. I asked, please plot 4 solutions that start here, 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 and I use green for it. And the computer found the solutions, and they are really straight lines. And then I put some other starting locations, and that's the blue curves. And as you can see, they are really curving so that they are hugging this line which is more flat, the dominant direction 2, 1. So our theoretical analysis is matched by the actual outcome, which is interesting. This was a typical example. What I mean by this, the combination of eigenvalues allowed us to hit one of those 6 situations. Let me show them again. Okay. So that's the 6 situations, and our example was representative of the upper left one. But I commented that these are not the only possibilities. There are also some, let's say, rare cases when things are still different. So the last example for today's lecture will be, again, a system of linear differential equations, but a non-traditional one. Let's see. Our last example is, again, a system which is 2 by 2. It's linear, and this time it's homogeneous. And because it's homogeneous, there is definitely a stationary solution, 0, 0. But let's do it properly. We take the right-hand sides, we make them equal to 0. X minus 3y is 0. X minus 3y is 0. Well, actually, that's a singular system. There is just one solution, which is y is equal to 1/3 x. It's one solution, but in 2D. It's a line of stationary points. So stationary points, in fact, look like this: x, 1/3 x, where x can be anything, any real number. There is infinitely many stationary points. Now let's put them on the board. Here is the trivial stationary solution, and all of them are along this line, y is equal to 1/3 x. These are all stationary points. Interesting. Now, because the system is singular, also the matrix of the system is singular, it means that one of the lambdas must be 0. And therefore, the trivial stationary point is unstable. And we know that because lambda is equal to 0 is not less than 0. That's the argument. Okay. Let's see. Our matrix A is 1, -3, 1, -3. We find the determinant of 1 minus lambda, -3, 1, -3 minus lambda, which is, let's see, lambda squared. Well, 3 lambda minus lambda is plus 2 lambda. Minus 3. Plus 3. This is lambda squared plus 2 lambda. And perhaps this could be 0. And the answer is yes, it's 0 if lambda is 0 or -2. So there is one direction where the solutions are not approaching the origin or going away. It's a stationary type of a solution, e to 0 times t. And then the second component in the fundamental system has e to -2t. Before we write the general solution, we should look at eigenvectors. Let's see. When lambda is 0, then the matrix we are looking at is, well, exactly this one. I use the first row to create my equation. V1 minus 3V2 is 0. So the eigenvector could be, well, let's see, I put 1 for V2 and 3 for V1. That's for lambda equal to 0. So my general solution is A times 3,1 times e to 0, which is 1. So I can leave it like that. Interesting. What is the vector 3,1? Well, that's exactly the vector which is giving our line. Well, perhaps this is not exactly 3 to 1, but it's supposed to be the one. So depending on what A I put in here, all these solutions are just dots. They are stationary solutions. So I get them not just by looking for stationary solutions, as I did at the start. I obtained them from solving this system, but I can also see them here in my formula for the solution. And then there is another component, and that's where things get interesting. Let's see, when lambda is -2, then we get the matrix 3, -3, 1, -1. Is it singular? Yes. So things are okay. I use the second row for my equation. V1 minus V2 is 0, and the vector is 1, 1. This is actually fairly routine. So my second solution has direction 1, 1, and exponential based on a -2. And of course, this part goes to 0. So all my solutions look like this. First of all, I fix some stationary solution, and then to this I'm adding another vector which is going in direction 1, 1, or perhaps -1, 1, depending on the sign of B, and it's multiplied by some number which is decreasing in size. So I choose my stationary solution, for instance, this one, and then I'm adding some component which is in the direction 1, 1. Direction 1, 1, that's the diagonal, which is about this. And this component is getting smaller and smaller and smaller. So the orbit goes like this. And if I start here, the orbit goes like that. And if I start here, the orbit goes like that. So these are the orbits. They have direction 1, 1. So, oh, okay. I slipped out. This should be 1, 1, direction 1, 1, okay? But okay, this is just a sketch. On the other hand, if I start here, again, I'm going in the direction 1, 1, and I'm going this way. Direction is 1, 1. What does it mean? Well, imagine that we are sitting at the origin and we move away a little bit. If we move in this direction, we return back along our orbit. But if we move in this direction, then the orbit moves us here. We never get back. And that's why this guy is unstable. And the same argument applies to all those stationary solutions. If I start at this stationary solution, and I displace my location, or let's say the bug is sitting here, and I displace the bug, then it will go in the direction 1, 1, which brings that bug to this location. Not here, but to a different place. So also this guy is unstable. All these stationary points are unstable. Now, this is a very strange picture for orbits, and we definitely do not see such a picture in our list. Because, as I said, these are typical situations, but there are also other possibilities. Fortunately, in applications, we generally do not get single matrices, so we do not have to worry very much about such strange situations, but they can appear. And we can see it for linear equations directly by analyzing our solution. And if our system is not linear, then perhaps we can use linearization. OK, the last trick. Here is Maple, and I will ask it again for some solutions. And you can see them here. The green curve, that's the solutions that are stationary. It's actually infinitely many stationary solutions, their orbits, because these solutions are stationary, and therefore their orbits are just dots. And then there are those blue curves. I started at different locations, and I was moving towards this green line in the diagonal direction, essentially. And you can see the arrows. They're all going in the diagonal direction towards the green line. So this is a new situation. It wasn't on our list, but because it's rare, we don't really care. And that's it. So this much for analyzing solutions of systems. And in the next lecture, we will ask how to get those numerical solutions, which I have been actually showing several times. So a good question is, where did I get them? Where Maple got them? See you there.